The headline says lithium is abundant, yet we still face battery shortages that stall entire industries. This disconnect exists because scaling supply chains has become a chemistry engineering problem, not just a mining volume issue. The bottleneck is no longer how much rock you dig up, but the energy-intensive roasting processes required to make it usable. Today, we follow the physical layer where new low-temperature extraction methods are bypassing this thermal barrier. We will explain why the industry must shift from brute force processing to precise atomic-level engineering and what that means for the future of hardware manufacturing. For decades, the narrative around lithium has been simple. There is enough in the Earth's crust to power a green revolution if we just dig it up fast enough. But this view ignores the massive thermal wall standing between raw ore and battery-grade material. The standard industrial process relies on high-temperature roasting, where ores are heated to extreme temperatures over long periods to separate lithium from impurities. This is not merely an energy cost. It is a fundamental physics constraint that limits how fast we can scale production globally. You cannot simply turn up the heat indefinitely without facing equipment degradation and astronomical power demands that outpace grid expansion in many regions. The critical shift happening now is that supply chain scaling has moved from bulk mining volume to precise chemical engineering of solid-state electrolytes like lithium thiophosphate or Li6PS5Cl. While traditional methods struggle with thermal management, new low-temperature extraction processes prove we can bypass the roasting bottleneck entirely by stabilizing ionic conductivity without requiring extreme heat conditioning. This changes the definition of a manufacturing constraint from how many tons per year to how precisely can we engineer molecular structures. The industry is no longer just digging, it is solving complex materials science challenges at the atomic level. Quick resource note. I keep a curated set of Amazon search links in the description for books, gear, and tools relevant to this channel's topics. Some are affiliate links, so I may earn a commission at no extra cost to you. Please consider supporting the channel by using those links if you find something useful. To understand why this matters, consider the specific failure modes that have plagued low-temperature performance in battery applications until now. Research indicates that ionic conductivity and ion migration barriers degrade significantly at sub-zero temperatures due to subtle lattice parameter variations. In simpler terms, as things get cold, the pathways for lithium ions to move through a solid material become blocked or distorted by microscopic changes in their crystal structure. These are not large mechanical failures, but atomic-level shifts that computational models can only simulate with immense expense and effort. For years, engineers focused on thermal dissipation and geometric optimization of battery packs, like trapezoidal configurations using phase-change materials to retain heat. This was a workaround for the symptom, treating the battery as a cold object rather than addressing the extraction process itself. The emerging breakthroughs suggest that we can now engineer the material properties directly during extraction, effectively creating an electrolyte structure that remains conductive without needing external thermal conditioning. Studies on solid-state systems reveal that dominant surface contributions and lattice variations are the primary drivers of this failure mode. By controlling these factors at the source through low-temperature chemistry, manufacturers can produce battery-grade lithium that is inherently more robust against temperature fluctuations. This moves the engineering priority from managing heat in a finished pack to preventing the formation of unstable structures during production. This transition highlights a fundamental change in how we view hardware scaling. The hidden problem is no longer just supply volume, but the nonlinear decline in ionic conductivity and ion migration barriers at sub-zero temperatures, which traditional roasting cannot fix without massive energy penalties. When you rely on high heat to force separation, you create materials that are often less stable or require further processing steps that consume more power downstream. By bypassing this thermal step entirely, the new extraction methods stabilize the solid-state ionic conductivity from the very beginning of the supply chain. This reduces waste and energy consumption in ways that simple volume increases never could achieve. Engineering teams must now prioritize these advanced material architectures over simple capacity scaling because the physics of low-temperature performance dictates whether a battery can function reliably in real-world conditions. If you extract lithium using methods optimized for high heat, you may end up with a product that works fine at room temperature but fails when exposed to cold environments. The new chemical fixes ensure that the material properties remain consistent regardless of external thermal stress. This is not just an efficiency gain, it is a reliability guarantee that allows manufacturers to deploy hardware in harsher climates without over-engineering cooling systems for every single unit. The implication for global infrastructure is profound. As we move toward electrifying transportation and storing renewable energy, the ability to produce battery-grade materials efficiently at scale becomes as critical as finding new mines. The constraint on scaling is now a question of chemical precision rather than geological availability. If we cannot solve these low-temperature barriers through atomic-level engineering, our capacity for deployment will remain capped by the physical limits of thermal processing. This creates a scenario where software and demand can grow exponentially, but hardware supply grows linearly or stalls entirely due to upstream manufacturing physics. We are witnessing a pivot from an era defined by excavation to one defined by synthesis. The ability to extract lithium without roasting represents a fundamental rethinking of the entire production workflow. It shifts the competitive advantage away from companies with the largest mines toward those with the most sophisticated chemistry and process engineering capabilities. This is the new frontier for hardware manufacturing, where success depends on mastering the behavior of ions at low temperatures rather than simply moving more rock through a furnace. The stakes here are high because the demand for batteries will only accelerate as we electrify everything from cars to grids. If we continue relying on energy-intensive roasting processes, we risk hitting a wall where power availability limits production faster than geological scarcity ever could. The new low-temperature extraction methods offer a path forward that decouples supply growth from thermal constraints, allowing us to build the infrastructure needed for a sustainable future without burning through our own resources in the process. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.